Jai students, so this is our 5th lecture in our complex lecture topic series. So the topic for today's lecture is programmable logic devices, ROM, PLA and PAL. So these are the 3 devices which can be used at our level to program or to design circuits or programmable circuits. That means we can change some part of those circuits, we can change the logic in a already existing circuit, and that circuit can act like a new circuit. That means a single circuit, after making some changes, those changes are the programmable changes. After making those programmable changes, that same circuit can act like in a different manner. Okay, so that means this is programmable. So far, whatever we have designed in our unit 2, we can design any circuit which we have designed in unit 2, full adder, full subtractor, code converters, comparators. All those functionalities can be realized using these ROM, PLA and PAL as well, with a certain extent of programmability. We will see that what is the extent of programmability in these 3. So let's start with the basic. PLD is introduction, then we will cover ROM as a PLD, and then PLA and PAL. Okay. So in recent times, small scale integration SSI and MSI, medium scale integration circuits, are replaced by more versatile PLDs. PLDs means programmable logic devices. Okay. So these are the 3 programmable logic devices which we are going to cover today: read only memory, programmable logic array and programmable array logic. So if we compare all these 3, we can see that in PROM is programmable ROM, AND array is fixed and OR array is programmable. Now what does this AND array and OR array means? Whenever we are provided with a SOP expression, something like that, AB plus CD, this AB is also considered as a product and this is a product, and both these products are summed. That's why it is termed as SOP. Further, if we see that this AB is an AND, this CD is also an AND, and after computing the AND of these 2 variables, what we are doing is we are ORing them. So this structure becomes AND OR structure, AND OR structure. So this SOP can also be termed as AND OR. Okay. Now that PROM is saying that out of this AND and OR, this AND is fixed and this OR is programmable. And why we have mentioned array? Because there will be multiple AND gates, so multiple AND gates collectively are termed as AND array, and similarly there can be multiple OR gates, those multiple OR gates are termed as OR array. So in a PROM, AND array is fixed. Why is it fixed? Because we are going to use a decoder. Okay, we are going to use a decoder, and if we recall that a decoder is a combination circuit which has multiple inputs and multiple outputs, and that relation is something like that: if there are n inputs, then there will be 2 raised to power n outputs. So this becomes n cross 2 raised to power n decoder. Now these 2 raised to power n outputs of this decoder are actually the 2 raised to power n AND gate outputs. Okay. So every output that is coming out of the decoder is actually the output of an AND gate. So for AND purpose, for preparing the AND gates, we are going to use a decoder. Okay. Out of this AND OR expression, for AND part we are going to use a decoder, and we can see that all those AND gates are not available to me externally. Instead, all these AND gates are part of this decoder and are available inside this decoder. So inside of the decoder is not programmable because it is already existing in form of a decoder. That means this decoder part, this AND part is fixed. I cannot change the AND part of this PROM. Okay, but once the outputs of these decoders are available to me, I can use OR gates here as per my convenience. So OR gates, how many OR gate I want to use, what all will be the inputs of those OR gates, that is programmable. So that's why we have mentioned here programmable OR array. Okay. Similarly, if we proceed further for PLA we say that AND array is also programmable, OR array is also programmable, and that is only possible if we are not going to use a decoder. Instead of using a decoder, we will be using standalone AND gates as per my requirement. What will be the input of that AND gate, that is also up to me. So all those changes can be, all those programmable changes in the AND part are manageable in PLA. Similarly, OR part is identical, because that OR part is programmable as similar to that PROM part. Once the AND gate outputs are available, number of OR gates and the inputs to the OR gates can be controlled by me. So that's why it is also programmable. But in case of PAL, AND array is programmable, but OR array is fixed. That means I can use the number of AND gates as per my convenience. I can decide whatever will be the input of the AND gate as per my convenience, but the output of AND gates will be connected in a fixed manner to the OR gates. That means the connection of OR gates cannot be changed once they are made. So that means OR part is fixed in PAL. So this is the basic difference between PROM or a ROM, PLA and PL. Now these are the basic classifications. This can be a separate question. What are the different types of PROM or what are different types of ROM, and how out of these which is convenient for me to be used as a PLD. So PROM is programmable read-only memory. Programmable read-only memory, that means user is allowed to program it as per his convenience. MPROM means mass PROM. That means once programmed by the manufacturer, not by the user. For example, we can take the example, whenever we purchase a printer or a scanner or any hardware component that is going to be connected with a PC, then along with that hardware, printer, scanner or anything, we are getting a CD which is carrying the driver of that hardware. So that CD, the driver it is containing, no further data can be written in that CD. Although space might be available, but that CD is masked for further programming. That means anything which has been written on that CD is written by the manufacturer at the manufacturer end, and user is not allowed to further write on to that. That is MPROM, mask programmable read-only memory. Then EPROM is erasable programmable read-only memory. Okay, erasable programmable read-only memory. Erasable means, that means once we have written the information, we can make changes to that as well. Okay, so that EPROM is the best candidate to be used as a PROM as a PLD, because once we have written something, we can also erase that and reprogram that as per my next application. Okay, similarly, then last one is EEPROM. EEPROM means electrically erasable. By electrically erasable, we mean that means in this EEPROM, the erasing mechanism must be something other than electrical. That is, ultraviolet rays are used for erasing the contents of the PROM. If UV rays are used for erasing mechanism, then it is EEPROM. But if electric current is used for erasing, then it becomes electrically erasable programmable read-only memory. So these are the basic classifications of ROM. Now coming to the designing using all these three. So we are going to design a full adder circuit using all these three, and we will notice that what are the different changes which are required to be incorporated while preparing the same full adder using PROM, using PLA and using PL. So for that we have to first understand what is a full adder, that we have already covered in our unit 2. So I am not going to the much details. So full adder is a combination circuit which accepts 3 single bit input numbers and prepares their sum and carry at the output. So for 3 variables, inputs can be 000, 001, 010, 011, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So 0 0 0 means sum is 0, carry is 0. For 0 0 1, sum will be 1, carry will be 0. 0 1 0, sum will be 1, carry will be 0. 0 1 1, sum will be 0, carry will be 1. Sum 1, carry 0, sum 0, carry 1, sum 0, carry 1, sum also 1, carry also 1. We are not going to details how this sum and carry are written because that is already covered in Unit 2 combinational circuits of our syllabus. So I assume that these full adder truth table is known to you, but for those who are taking this circuit for the first time, we are simply adding these 3 bits and calculating the sum and carry and mentioning them as the output terminals sum and carry. So from this, to design circuits using ROM, as the AND part is fixed, that means we need not to solve any expression if we want to design a circuit using ROM. We just need the minterms. So for this sum, we can check that the terms are this 1, 2, 4 and 7. So 1, 2, 4 and 7, these are for sum. Similarly for carry, my minterms will be 3, 5, 6 and 7. 3, 5, 6 and 7. Okay. So we need not to put these minterms into a K-map and solve the K-map to get the minimized expressions, because minimized expression will not be canonical, because for full adder design we will be using a decoder, and in a decoder the AND part is already prepared inside the decoder. So we need not to recalculate using K-map or obtain the minimized expression. We can simply proceed with the minterms and realize the circuit directly using a ROM. But what is the ROM to design circuit using ROM? A decoder is required. What will be the size of the decoder now? So simple funda is that you have to choose a decoder with number of inputs equal to number of inputs in application to be designed. So we are going to design a full adder. So application to be designed here is a full adder. Okay. And full adder has how many inputs? 3 inputs. So these 3 inputs must be the number of inputs with in a decoder. So that means a decoder with 3 inputs. So a decoder with 3 input will be 3 cross 8 decoder. So that's how we can select the size of a decoder to realize any application. Okay. So once it is now known to me that we are going to use a 3 cross 8 decoder, we can proceed with the circuit. So let's take a 3 cross 8 decoder. There will be 3 inputs. 3 inputs will be my circuit's input A, B and C in. This will be a 3 cross 8 decoder circuit which will be giving me 8 outputs. So 0, 1, 2, 3, 4, 5, 6 and 7. Okay. So these are the 8 outputs. Now that AND part is already taken care of inside the decoder. We just now need to use the OR gates to complete the circuit, and for OR gates, that means to produce the sum, that summation is representing OR gate, and all these 1, 2, 4 and 7, these are representing 4 products or 4 AND gates. Okay. So now the output of these 4 AND gates, AND gate number 1, 2, 4 and 7 need to be added using an OR gate. So 1, 2, 4 and 7. So we have drawn a vertical line. Out of this, on this vertical line, 1, 2, 4 and 7, these 4 are going to participate and are going to be added using an OR gate to produce the sum. So now this cross is denoting a programmable link. That cross could have been placed anywhere on these 8 possible places from 0 to 7. Out of these 8 possible places, I can choose 1, 2, 3 or all 8, okay, as per my requirement. So in this case, we have seen that 4 things were required to produce the sum. Similarly, if we check the carry part, so output of AND gate number 3, 5, 6 and 7, which are already prepared inside the decoder. So 3, 5, 6 and 7 are also going to be added using another OR gate 3, 5, 6 and 7. So this is full adder design using ROM. That means this multiple AND gates are taken care of by using programmable version of the AND gates. So what we can remember is, we had used these kind of circuits. A, if we want to use, then we had used like this produced the A bar and this produced A. So similarly, AND gate, if we had to use triple input AND, we had used like this A, B and C. Similarly, triple input OR, if we wanted to use in second unit, these are all concepts of unit 2, like we had used these structures in this manner. But in case of programmable part, this can be replaced by this, okay. This will represent A bar and this will represent A. Now this thing can be replaced by, and there will be 3 vertical lines A, B and C, and all 3 will enter the AND gate to produce the output. Similarly here, there will be an OR gate. So this we have to remember, that the circuits shown in red are the basic versions which we have already used in unit 2, and these are going to be replaced with these 3 while designing their programmable version using ROM, PLA and PL. So out of this we have used this thing here and here as well, okay. So now we will design the same circuit of full adder using a PLA, okay. So full adder design using PLA. Now for this we need to minimize those expressions, because AND gates are going to be chosen by me only, and these are not going to be inside the decoder. I am not going to use a decoder now. Instead I will be using separate AND gates as per my requirement. So for this I need to solve these expressions and see out, which we had earlier obtained. Now we are solving these using K-map. Input variables are A, B and C in. So this is my K-map layout. Feeding these minterms. So first we are preparing the layout. Now feeding the minterms. 1, 2, 4, 7, 1, 2, 4 and 7. We can see that no grouping is possible. That means these 4 will be separate. So we can write sum as A bar, B bar, C in plus A bar, B, C in bar corresponding to 2. Then 4 A, B, C in bar corresponding to 4, and then 4 will be 1, 0, 0, and then 7 will be A, B, C in. Okay. Similarly, preparing the K-map for C out. So in short, I will be solving this 3, 5, 6, 7. That means 3, 5, 6, 7. So there will be 3 groups, and we can write the expression for C out or carry. Simply carry we can also mention. C out or carry are identical. The C out is representing the final carry. Okay. So this comes out to be AB plus BC in plus AC in. Okay. So these are the expressions. Now in that we can see that there are, let's mark our products in this. So this is product number 1, this is product number 2, this is product number 3, this is product number 4, and this is product number 5, this is product number 6, this is product number 7. So we can check that a total of 7 AND gates are required. Okay, a total of 7 AND gates are required for 3 input variables A, B and C. So now let's design the circuit using PLA. So I am requiring A. So this will be my A, similarly B, similarly C in. Okay, I am slightly increasing the length because I need to place 8 AND gates. Okay, now placing the AND gates. So I place 8 vertical wires where 8 AND gates will be connected. Sorry, I will be requiring 7 AND gates actually, isn't it? So we have 7 AND gates, not 8. So I am removing this extra 8th wire. AND gate number 4, 5, 6 and 7. Okay, and we are going to use 2 outputs. So there will be 2 OR gates as well. Okay, I will be using 2 OR gates. Okay, so first AND gate, product 1, A bar, B bar, C in. So A bar, this is A bar, this is B bar and this is C in. Second product, A bar, B, C in bar. So this is A bar, this is B, this is C in bar, sorry. Okay. Now third product is A, B bar, C in bar. This is A, this is B bar, this is C in bar. Fourth product is A, B, C in. A, B, C in. Fifth product is A, B. So this is A and this is B. Then B, C in. This is B and this is C in. Okay, this is C in here. Then third, last product, this one is A, C in. So this is A here and C in here. So these are the 7 products. Out of this we can see that these 4 products are going to be added together using this first OR gate to produce the sum, and the next 3 products are going to be added to produce the carry, or we have named it as C out. Okay, so the same full adder circuit is designed using PLA in this manner. Okay, so now circuit designing using PLA is very much simple. Full adder circuit design using PAL. Okay, using this PAL, that means programmable array logic. Now going back slightly, what is this PAL? Programmable AND array. That means AND part is still programmable, but this OR part is fixed. That means the inputs to the OR gate cannot be changed. There cannot be a cross at the input of OR gate because that is not programmable. Okay. So let's see how we are going to proceed with that. So for PLA we have seen that AND part is programmable, AND is programmable, and here we can see that this OR is also programmable. Okay, but now for PAL same steps are to be repeated. We have to solve K maps, we have to find the expressions, we have to find the number of products. That AND part is programmable and same as PLA. Okay, so this thing is completely same. Now only thing which is going to change is these crosses. There cannot be these crosses on the OR part. So these crosses are going to be replaced with permanent connections like we had done in unit 2. So there cannot be cross, instead there will be permanent connections. So I am denoting them as a filled dot which denotes a connection in our circuit. That means these 4 things are going to be added to produce sum, these 3 things are going to be added to produce a carry. Now if you want to design a full subtractor, okay, if you want to design a full subtractor, products will change, but in a full subtractor as well the difference will be identical. First 4 things will be, the sum of first 4 products will produce the difference and the sum of next 3 products will produce the difference. That means even if this OR part is fixed, the same circuit can be reprogrammed at the AND level, okay, to make a full subtractor. Here in case of PLA, AND part is also programmable, OR part is also programmable. That means a PLA can design any circuit with 3 inputs which require 8 products and 2 outputs. Okay, but a PL can realize any circuit with 3 inputs, 8 products, 2 outputs, but there is a constraint that those 2 outputs can only be in form of, first product will be sum of 4 things, second product will be sum of 3 things. There is a constraint associated with this PAL now because the OR part is not programmable. So this is the difference, basic difference between ROM, PLA and PL. How these 3 different programmable logic devices can be used to realize any circuit using these ROM, PLA or PL. Okay. So with this we come to the end of today's lecture, and these 3 devices can be used to design any other circuit like code converters, two-bit comparator, parity checkers or generators, etc. Okay, each will be requiring different number of inputs, different number of outputs, and we have to choose carefully that what size of decoder. In case of ROM we will be using the decoder, what will be the size of the decoder. In case of PL and PL we have to choose number of AND gates and number of OR gates as per my requirement. Okay, so with this we come to the end of this lecture. Thank you very much.